is a two-step process. First, we must record the hologram, and then we must reconstruct it. These are Gabor's original drawings, illustrating both his ideas for recording and reconstructing holograms. So as I stated earlier, we have a point source of light, which is recorded after scattering from objects to form an interference pattern, which he called a hologram. Then his idea for reconstructing this hologram was to physically recreate a reference wave and shine it through a hologram, resulting in an interference pattern which we can focus through a lens to give an image of our scattering object. The problem with this, of course, is that there was no magnification. And so his only solution was to make an enlarged copy of our hologram before reconstruction, then pass our light through and focus it into the object. The modern method of reconstruction, as developed by Dr. Kreutzer, can be thought of as focusing at a given depth. We simply have to track our wavefronts back to the object, and the image is given. Another great thing is we can track our wavefronts back from the screen and take many slices along our object plane to yield the object in 3 dimensions. So this is an example of a hologram. As you can see at this point, we don't know exactly what it is. It's simply an interference pattern. But this 2-dimensional image holds the entire 3-dimensional information of the scattering object. So upon reconstruction, we can see what it is. In this case, it's the head of a fruit fly. Hopefully everyone can see that all right. And here you can see the resolution capabilities of the microscope resolving all of these small hairs along the head. So why do we bother with holographic microscopy? And what sets DHM apart from the crowd? Well, a conventional compound microscope has the ability to view objects on extremely small scales. However, the smaller the scale, the smaller the depth of field. And so if we want micron resolution, then we can only focus in on objects in a slice typically 1 to 2 microns thick. And this isn't a problem if the objects we wish to view are stationary. However, if they're moving, it's extremely ineffective as they'll always be moving in and out of our focus depth. DHM, on the other hand, records objects without even focusing. And the depth of field is much greater, on the order of millimeters for micron resolution. Therefore, we can easily view objects in motion. DHM is also not limited to taking single holograms, but capable of taking videos, therefore giving us not only 3-dimensional but 4-dimensional imaging, as now we can study the movement of these small objects. As I stated earlier, a single hologram, is just a 2-dimensional image, but it holds the entire 3-dimensional volumes of information. Therefore, holography is not only effective, but economical, as we're storing huge amounts of data in a single 2-dimensional image. So because of these qualities, DHM fills a gap in the technological market for underwater imaging of objects on the micron scale. And because of its simplicity, it does so in a cost-effective manner. So before I was talking about Gabor's idea for physical reconstruction of holograms, now I'm going to try and show you the physics behind the numerical reconstruction and the mathematical reconstruction. So a common question in Fourier optics is finding the complex wave amplitude after light is scattered from an object or through an aperture. And the answer based on our reconstruction is, our geometry is given here, where U of psi is simply our complex wave amplitude at the screen, or our CCD chip, and U of r is the complex wave amplitude at any other plane before the screen. So all this means is if we know what the complex wave amplitude is at our screen, or our CCD chip, we can calculate it at any other point in space we want. The problem with this, of course, is we don't measure the complex wave amplitude. We only measure an intensity image, so the phase is lost. We don't know what that is. And so we can resolve this problem by taking inspiration from Gabor's original idea of reconstruction, which was to shine the reference wave back through the hologram, after which point it was focused into the object. And so we can represent this quite simply by a multiplication of our hologram, given here by I of psi, and our reference wave, which is just the wave coming from our point source. And for our scenario, namely that of a small scattered amplitude compared to reference amplitude, is approximately equal to our original wavefront. So this leads to the basis of our mathematical reconstruction, where U of psi here is simply our hologram, which is just the 2-dimensional image recorded on our CCD chip, and K of r is our reconstructed wave amplitude. So I'm not going to show you all the math as in any physics problem. There's a lot of pages of math, but this is the final solution. And the main point to take from this is that the magnification is decided by the user. Unlike a bore, we can reconstruct with arbitrary magnification. So our large delta X and delta Y here are simply the dimensions of the pixels on our CCD chip, and the dx, dy scattered around there are the dimensions of each pixel on our reconstructed image, which again the user picks based on desired magnification. Another great consequence of this is we can easily measure the size of objects on our reconstructed image. So this slide is pretty scary, and I'm not going to explain it other than to say it's the analytic solution to our reconstruction problem. And the great thing about this is not only can we reconstruct physical objects from experiments like cells and whatnot, we can model how the microscope acts under different conditions. And this is increasingly important in the research environment. So one important consequence of that is, of course, measuring and modeling the resolution capabilities of our microscope under different conditions. So it can be shown that the resolution limit in the xy plane is given by lambda over 2na, whereas the zx or the zy plane is given by lambda over 2na squared. Remember, we're looking at a three-dimensional volume. So this corresponds to our width at half max of an infinitesimal point scatter calculated via our analytic result. And all this means is if we have a point scatter or any scatter that's smaller than our resolution limit, it will always show up with a finite width, namely that of our resolution limit itself. And of course, two objects cannot be resolved if their distance is smaller than the resolution limit. So that's obviously the regular consequence. So this is a video showing kind of the depth resolution capabilities of the microscope. Here there are actually only three diatoms swimming in different directions. One's here, one's going across the screen, and one's going up. However, many holograms were added together to show the full path. And so each frame in this video is actually taken at a different depth. So we can see each of these little diatoms coming in and out of focus. This is another great image that I like quite a lot. It was taken from an experiment in the lab with latex beads. So these two beads in the center are about 80 microns in diameter, and these smaller ones are about 5 microns in diameter. And here we can clearly see the streamlines around the two large stationary beads as the 5 micron beads flow by. Of course, regular imaging is no problem with DIHM. It shows up just like any other camera. Sorry, you can't see that quite as well as I can here, but as I said, it's just like any other camera at this point when we're just imaging in a single plane. And of course, the speed is given just by our exposure time of the CCD chip, which the user picks. So this image shows the swim path of the diatom from the last video. And images like this are actually taken or compiled by successfully adding and subtracting holograms in series, so we can see our full swim path. So images and objects, or images and videos like these would be incredibly difficult to get with a conventional compound microscope, because we would have to continuously be focusing to get the objects. So the great thing about DIHM is we don't require any focusing while taking images. All of that is done at a later date on the computer. So what this means is that DIHM doesn't require any interaction while collecting data. We can simply drop our microscope to the bottom of the ocean and let it record data while we're watching TV. Then when there's a commercial, we pull it up and take a look at our new discovery. Thank you very much.
Do you have any questions?
Yes?
Do you see this being used primarily in marine biology?
Biology is one of the main applications for it because there are really no other microscope can image, micron-sized objects underwater. And so that's one huge application of it. There are several papers published using this microscope taking images at like 6,000 meters. And so that's a huge application. Of course, the Bohr wanted it to be used with electrons. So for our reference wave was actually an electron wave. And that's also being developed now. And of course, you get much better resolution. For light, it of course depends on the wavelength of light we're using, but for electrons, we're currently getting around nanometer resolution with the microscope. So, yeah. Questions, judges, please? Yeah.
Can you elaborate some more about the interface sensitivity?
sensitivity. Okay, so phase doesn't really come into it. We're only recording an intensity image. And so this is one of the problems that Gabor had, especially with this idea of electrons. So if we're reconstructing an image that was taken with electrons, do we need to use an electron beam to reconstruct the image, or can we use a plain light beam? This doesn't seem to come into play at all when we're reconstructing, at least numerically. It's never been tested whether, the physical reconstruction of, shining an electron beam back through a hologram to reconstruct the image. So the phase doesn't come into play at all.
So materials with similar refractive indices would be hard to show on this.
Well, yeah, so the idea, at the beginning, I kind of proposed a question that, if we record a shadow, can we reconstruct what the object is? And that all depends on kind of the density of whatever object we're viewing. So if we took a picture of, our own shadow on the street, we couldn't reconstruct what our face looks like. You could only reconstruct like an outline. But for objects that are transparent or semi-transparent or very thin, the method is very great. So for the electron case, we're testing a lot with graphene